All right, let's get into it. Today, we're going to tackle one of those exam questions that, let's be honest, can look pretty scary at first glance. We're going to break down a 5-mark bounds question piece by piece, and we'll use the official mark scheme as our secret weapon to make sure we nail down every single point. Okay, you ready? Let's dive in. So here's the puzzle we're up against. We've got this equation for t and 3 variables, w, a, and c. But, and this is the most important part, none of these numbers are what they seem. They've all been rounded. So our job is to work with that little bit of uncertainty, that fuzziness, to figure out a reliable value for t. Think of it less as a math problem and more like a detective story about precision. So here's our game plan. We're going to crack this thing in 5 simple steps. First, we'll set the scene with the main challenge. Then we'll decode the clues in the question. After that, we calculate the absolute limits for each number, use them to find the final range for t, and finally, pick out the perfect answer. Okay, so the most important part of the whole question is this little phrase right here. By considering bounds, calculate the value of t to a suitable degree of accuracy. This is a huge clue. It's telling us we can't just, plug the numbers into the calculator and call it a day. We have to dig deeper and find the absolute maximum and minimum that t could possibly be. Before we even think about touching that calculator, we have to put on our detective hats. The clues are hidden in plain sight, in phrases like correct to the nearest 5 and correct to 2 significant figures. These aren't just descriptions, they are literally the keys to unlocking all 5 marks. They tell us exactly how much wiggle room each number has. So let's get this straight. What even are bounds? Well, it's pretty simple. The lower bound is the absolute smallest number that would still round up to our value. And the upper bound? That's the cutoff point, the smallest number that would round up to the next value. So the original true number could have been anything in between. All right, so how do we actually find these bounds? It all comes down to a simple rule. Find the degree of accuracy, chop it in half, then add and subtract that from your number. So for W, it says to the nearest 5. Easy. The accuracy is 5, we have it get 2.5. For A and C, it's 2 significant figures. Well, for 9.8 and 2.5, that second digit is in the tenths place, which is 0.1. We have that to get 0.05. That's what we'll be working with. Right. Enough theory. Let's actually do this and start bagging some of those marks. On the next slide, you'll see how we lay this all out and find the upper and lower bound for all 3 of our variables. And boom, here are the bounds all calculated out. For W, it's plus or minus 2.5. For A and C, it's plus or minus 0.05. And get this, the mark scheme says if you find just one of these 6 values correctly, you've already earned your first mark. That's a B1 mark in the bag. Super easy point right there. All right, now for the main event. We've got the limits for our individual ingredients. Now we need to combine them using our formula to find the absolute highest and lowest possible values for t. This is where we get those big, juicy method marks. Okay, quick question for you. Think about it for a second. T is a division. If you want the smallest possible answer from a division, what do you do to the number on top and what do you do to the number on the bottom? You got it. To make t as small as possible, you need the smallest possible number on top. That's the lower bound of w. And you need to divide it by the biggest possible number on the bottom. To make a minus c as big as possible, we need the biggest a, and we have to subtract the smallest c. That's why we use the upper bound of a and the lower bound of c. So let's plug those numbers in and see what we get. We take 432.5 and divide it by 9.85 minus 2.45. This gives us a lower bound for t of about 58.4459. And by the way, just writing down this exact setup is what gets you a method mark, even before you calculate it. Okay, let's do the flip side. To get the largest possible value of t, the logic is just the complete opposite. We need the biggest number on top we can get, the upper bound of w, and divide it by the smallest number on the bottom. And to make a minus c as small as possible, we take the smallest a and subtract the biggest c. Let's run the numbers on that. 437.5 divided by the result of 9.75 minus 2.55, and that gives us an upper bound of about 60.7638. And just like that, by getting both of these calculations right, you've locked in the main method and accuracy marks. We are so close now. Okay, we have done the really hard work. We know the absolute territory where t has to live, but the question wants a single value to a suitable degree of accuracy. So now it's time to bring it home and grab those last 2 marks. So, what have we actually found? We've proven, mathematically, that the true value of t has to be squeezed somewhere in between 58.44 and 60.77. Just getting to this point and writing down this range, that's another mark, an A1 accuracy mark, right there.
Okay, so take a good look at that range, from 58 point something up to 60 point something. What single, clean, sensible number would you say is a suitable answer that fits in there?
It's gotta be 60, right? It just feels right. And that answer gets you the final accuracy mark. But wait, just writing down 60 isn't enough. For that final, crucial communication mark, you have to explain why. And this is the golden sentence that gets you that final C1 mark. You need to find a degree of accuracy where both the lower bound and the upper bound agree. So let's try rounding to one significant figure. Our lower bound, 58.44, rounds to 60. Our upper bound, 60.76, also rounds to 60. They meet in the middle. Because both limits point to the exact same number, 60 is our suitable answer. That is the watertight justification they're looking for. And there you have it. We cracked the code. What started as a tricky math problem is really about understanding the limits of what we know. It really makes you think, doesn't it? How many of the numbers we trust every single day, in the news, in scientific studies, have these hidden ranges, these hidden bounds that could actually be telling a completely different story? Something to think about.